That's Siddharth for all of you. So Siddharth is deeply passionate about mathematics, needless to say, and he's a fifth grader. He comes from Pondicherry or Puducherry, and he studies in the Study Licol International in Puducherry. Apart from mathematics, he loves physics. He loves coding. He loves eating. So he's a foodie. He plays the piano. He plays the keyboard, and he's famous for a lot of his signature jokes in our Kaprekar batch. So Kaprekar batch is one of the batches of Ganit Manthan, and Siddharth has been part of that since over a year. And I have to say that he is a true mathematician at heart. And we always exchange a lot of ideas related to mathematics. So Siddharth, we are very happy that you have agreed to share some ideas with us. Without taking more time, I'll hand it over to you. Over to you, Siddharth. You can.
Good evening, everyone. I am Siddharth Laxmisha from Kaprekar batch. I am 9.5 years old. Today, I am going to talk about the units in physics and compare them with the units of astronomy. Because this subject is so vast, I limit myself to the concepts of length, mass, volume, time, shape, and temperature. They answer the questions: how far, how heavy, how big, how fast, and how hot. Now, with your permission, I shall start. Let's go to distance. On Earth, we use a ruler or a tape to measure lengths, the unit being inch, centimeter, mile, kilometer, etc. What about in space? Can we use the same units? No. Just take a look at these values. These are the distances of planets from the sun. These values range from 35 million to 2 billion. So clearly, kilometers is not an appropriate value to use. We need different units. Now, how far are stars from Earth? Proxima Centauri, the closest star after the sun, is 40 times 10 power 12 kilometers from us. Barnard's star, the next closest star, is a faint red dwarf, about 59 times 10 power 12 kilometers from us. Wolf 359, the next closest star, is located 77 times 10 to the power of 12 kilometers from us. Now, forget stars. Let's go to galaxies. Canis Major dwarf, the nearest one to our Milky Way, is 25 times 10 power 16 kilometers away. Centaurus A, the known father's galaxy, is 12.1 times 10 power 19 kilometers from us. Ursa Major 2 dwarf, the Indian Saptarishi, is 9.8 times 10 to the power of 17 kilometers from us. So we can see these values: 10 to the power of 12, 10 power 16, 10 power 19. So clearly kilometers is not appropriate. We really need different units. Now, how do we measure these large numbers? To measure them, astronomers use a baseline of one astronomical unit, which is the average distance between the Earth and the Sun. 1 AU is actually the average of the Earth's major and minor axes in Earth's elliptical orbit. It is 1 AU is 150 million kilometers. But still, AU is small considering the vastness of the universe. Next higher unit is the light year. 1 light year is the distance light can travel in 1 year. 1 light year is 9.46 times 10 to the power of 12 kilometers. The next bigger unit is the parsec. 1 parsec is 3.26 light years, which is 30.84 times 10 to the power of 12 kilometers. Now, do decimals count at all? Here's case 1. No importance for decimals. In this huge, gigantic ocean of numbers, decimals have absolutely no importance at all because the numbers are so big. Case 2. Extreme importance for decimals. On the other side of the numbers, degrees and radians exist. They require a huge accuracy to the tune of arc seconds. One has to be as precise as possible in expressing arc seconds because even a minute error, if you extend the arms of the angle, if you extend the arms of the angle, when they reach the actual point, where they reach will be billions of kilometers away from the actual target where we want. Now, here are some astronomical facts. The universe is so vast, even imagination fades. It is so beautiful and big. We may not be seeing the birth and death of stars in our lifespan. We may be getting light still from dead stars. Stars like Eta Carinae or Betelgeuse, for instance, may have already exploded and ended its life, but still we see them. We have yet to receive the light from some newborn stars. As their distance is billions of kilometers away, light is on our way to reaching our eyes. Now, let's go to mass. If you weigh 25 kilograms on Earth, you weigh a whopping 63.3 kg on Jupiter, which is enough to make your bones crush under your weight. And you weigh a mere 9.5 kg on Mercury and Mars, and a mere 4 kg on the Moon. So you can jump at least 6 times higher on the Moon when compared to the Earth. Now, how to measure the mass of a star? Mass of a star is directly dependent on its temperature because larger mass stars burn hotter than smaller ones. How to measure the temperature of a star is covered in coming slides. And the mass of a star goes on changing with age because the stars keep on burning and burning. Here is an image of the life cycle of a star, starting with a stellar nebula. Now, let's go to volume. Here is a list of the planets by volume in descending order. Jupiter's radius is 71,492 kilometers, and Mercury's radius is a mere 2,440 kilometers. So just imagine how many Mercuries you can put in Jupiter. Now, here's a slide of imagination. Imagine you yourself. The world population is 7.8 billion people. And Earth is only one of the planets in the solar system. And the Milky Way has billions of stars like our sun. And millions of galaxies make this universe. So, you surely must be thinking, how big is our universe? How small we are. Now, let's go to time. How long is a day in planets? That is the time for one rotation around their axis. Jupiter takes only 10 hours to rotate around its axis, since even though it is the biggest and the heaviest planet, and Venus is the slowest planet, it takes 243 Earth days to rotate around its axis. Now, how long is a year in planets? That is the time for one revolution around the sun. Mercury takes only 88 days to revolve around the sun, and Neptune takes 165 years. This makes sense because the revolution period is directly dependent on the distance from the sun. And keep in mind, all of these values are in Earth days or Earth years. Now, let's go to temperature. Here is a list of the temperature on planet's surface. Venus This temperature is 470 degrees Celsius, extremely hot. And Neptune is minus 200 degrees Celsius, freezing cold. And now look at the range, 470 all the way to minus 200. Now, in the previous slides, we said that the mass of a star is directly dependent on its temperature. The temperature of a star is in turn directly dependent on the star's color. Astronomers calculate the color of a star using two filters known as the BV color index. B stands for blue light, V stands for visible light, green to yellow light. Here is a list of star temperature and star color. So if the star temperature is 4000 to 6000 Kelvin, then it will be yellow in color. Now finally, let's end at the shape. The shape of the universe is probably a Fibonacci spiral. I trust everyone knows what the Fibonacci series is. And why do I say it's a Fibonacci spiral? Probably because there are tons and tons of examples you can find on Earth. Even a seashell, an egg, and even a fetus in the womb, a cactus, a hurricane, and even the Milky Way galaxy. Scientists believe that our universe is ever expanding as a Fibonacci spiral. Keep in mind, I say probably a Fibonacci spiral. Any questions? Thank you.
Thank you, Siddharth. Thank you for that wonderful presentation. We have Arush who has raised hand, and others, those who have a question to ask to Siddharth, you can do a raise hand, and I'll unmute you. Arush.
That was a good presentation, Siddharth, but I have one question. How come Mercury isn't the hottest planet? I thought Mercury was the closest planet to the sun.
Well, that's a good question. Mercury isn't the hottest planet because it does not have an atmosphere to keep the heat. It does not have an atmosphere to keep the heat. Thus, Venus is the hottest planet instead of Mercury.
And there is Ashwath who has raised his hand. But before that, Siddharth, I had a question, Ashwath, if I may quickly ask. So Siddharth, can you tell us about how did you fall in love with stars and planets and space? When was the first time you got excited about this? Something about that.
That's easy. I got excited when I first went to the terrace, seeing all the stars. And one more thing. My father has downloaded an app. I don't remember its name. And when you point it to a star at night, it will tell you the name of the star. I used that quite a lot earlier. Okay. I used that quite a lot.
And that really, maybe.
Yeah, that really kind of fascinated me, and
Very nice. Okay. Ashwath.
Hi, Siddharth, this is Ashwath here. A really wonderful session, I must say. It's so good to see someone so interested in astronomy at such a young age. I can really relate with what you said right now, that you just fell in love with astronomy when you saw the stars. One thing I'd suggest is you check out this app called Stellarium if you're on a laptop. If you have a laptop, check this app called Stellarium. It's a laptop version of the app you mentioned that is that you use to find stars. It's much more detailed and much more interesting. But
I think that's the app that is. I don't remember the name though.
So wonderful session, really enjoyed it. Keep it up. Awesome.
Thanks.
Thank you, Ashwath. Ashwath, if you can just put the name on chat as well, it will be useful for others as well. So until we have any more questions, I have another question, Siddharth. So Siddharth, you might have heard about this intergalactic, Virgin Intergalactic Airlines, where people have started going to space, right? So I just want to put a hypothetical situation that what if we all or many humans start shifting to different planets in future. What do you think about that? What do you feel about that idea?
Well, that would be an excellent idea. Yeah, but yeah, that's an excellent idea and pretty good one too, because if Earth were ever to kind of die in a collision or something like that, that would be useful.
At least some of us will survive.
At least some of us will survive. Though I don't know who and who may not. I have no idea currently.
Okay, that was a good one. That was a good one. Anyone else? Any other questions before we move on to the next speaker? Johan. Yes, Johan.
What is an arc second? Like he was discussing that in the presentation.
Yes.
An arc second is basically it's a unit of time smaller than a second. Smaller than a second.
Okay.
Oops. It's an angle measurement. Sometimes I get confused. It's an angle measurement. It's related to angle measurement.
Do you know
Okay.
how small is the arc second, Siddharth? If you can explain that, or if you don't know, it's all right.
Actually, kind of don't know what it is, but I'll get back and let you know.
Okay.
Okay.
So, if I may, Johan and Siddharth, so what we have is a angle, a degree, we know, right? So if you split a degree into I think 60 equal parts, then you get a minute, and
Yeah.
if you divide that minute to 60 equal parts, you
Yeah.
get a second. And this minute and second is not the minute and second that we have in
Yeah.
time.
Yeah.
This is a different one. Yeah. Okay.
Thanks.
Thank you, Johan. Next, Swasti.
Yes, I had a question. So, how do you so the astronomers can't go to another planet and then measure the distance between Earth and a planet. So, how do they measure it? How do they come up with the numbers?
They come up with the numbers using some similar triangles from two different positions. They measure the angle using they measure the angle of elevation to the planet from two different places, and then everything's simple trigonometry to solve.
Okay.
So at two different places, they take two different rays, one ray to the planet, another ray to the planet, measure the angle of elevation. Same thing they do with another place, and then everything's trigonometrical. Yeah, you can use the sine and cosine rules.
Yeah.
Yeah, but we could see how deeply you are passionate about this area, and we could feel that passion when you were excited, especially towards the later part of the presentation when you were comparing temperatures, volume, and all that. So thank you very much for sharing this.